Assalamualaikum and hi to all. So this is the introduction of the heat transfer BMCG4743. So this is the outline of the subject. Okay, we will start with the introduction, which is for today lectures, and then we go to the heat conduction, forced convection, natural convection, thermal radiation, condensation and boiling, and last is the heat exchanger. Okay, so this is the objective of this chapter, which is to understand how thermodynamic and heat transfer are related to each other, perform general energy balance as well as surface energy balance, understand the basic mechanism of heat transfer, which are conduction, and the law is the Fourier law of heat conduction, convection, the law is Newton law of cooling, and radiation, which is Stephen Boltzmann law of radiation. And then identify the mechanism of heat transfer that occurs simultaneously in practice, and last is the solve various heat transfer problem encountered in practice. Thermodynamics and heat transfer. So this is basically the relationship between heat transfer and thermodynamics. So before we go further, we need to understand the terms that we use in thermodynamics and heat transfer, which is the first is the definition of heat, which is the form of energy. Heat is a form of energy, which is happen due to the temperature difference. It can be changed form into different things, but in this heat transfer, we are interested in the heat energy. And then the second one is the thermodynamic, which is the concern of amount of heat that being transferred as it goes from one system to another system until it reach equilibrium state. So in the thermodynamic, we are interested in the amount of energy. Okay? And last, the third part is the heat transfer, which we deal with the definition of the rates of such energy transfer as well as variation of temperature. So in the heat transfer, we are interested in the heat transfer direction. Okay, the direction of heat goes from one location to another location. And we're also interested in the time taken for the heat to be transferred from location A to location B. So that's why it has rates in it. And the same thing for thermodynamics and heat transfer. Okay, the heat is always from the higher temperature medium to the lower temperature medium, which is followed by the second law of thermodynamics. And okay, heat transfer stop when the two systems reach the same temperature, which is the same as the equilibrium state. So whenever both systems has same temperature, will reach the equilibrium state. So there will be no heat transfer happen if this case happen. Okay, and then last is the heat can be transferred in three modes. So basically we have three modes of heat transfer, which is conduction between contact of solid body, convection between fluid and also solid body, and radiation without any medium to transfer heat. Okay, so these are the examples of heat transfer and thermodynamic. Okay, the first one is figure 1.1, which is the thermos bottle, and the second one is figure 1.2. Basically, in the figure 1.1, we are interested in the heat transfer. We are interested in the direction, the time taken for the hot coffee inside the thermos bottle to be cooled down to the environment temperature. And the second one, we are interested in the direction of heat, which is from the high temperature side to the low temperature side. The importance of heat transfer. So in most cases, actually in our daily life, we happen to come across with most of heat transfer problem. Okay, so this basically part of it, which is from the electrical engineering side. We have design of cooling system of motor, generators and transformers. In the chemical engineering, we are concerned with the evaporation, condensation, heating and cooling of fluid. Basically, this happen due to the science of heat transfer. Okay, civil engineering, understanding the law of heat flow is important in the construction of dam structures. Okay, we need to know the direction of heat so that we can design, we can try to avoid the thermal heating and so on and so forth. And last is the mechanical engineering in the internal combustion engine, steam generation, refrigeration, heating and ventilation, and architecture in the design of buildings. So basically, in all these field, we have encountered with the heat transfer problem. Application areas of heat transfer. So this is the example of the heat transfer application in the human body. So we wear thick clothes in the cold environment. or the four season, such as in the winter season. So we will wear thicker clothes so that we can keep our body warm. So that's a part of the heat transfer. In our air conditioning system, we have this where heat being transferred from one location to the another location. We want to cool down a room, so we use the heat transfer application and sign of heat transfer to design the room to be cooled down at certain temperature. Okay, heating system. If you want to increase the temperature of a certain location by using heat pump and so on and so forth, we also apply the heat transfer theory of heat transfer. Okay, electronic equipment, we want to reduce the heating that happen in the electronic equipment. We use heat transfer. We have cooling, liquid cooling. We have also fan and so on and so forth. Power plant, basically most of the power plant equipment use heat transfer to transfer heat from one location to another location and to change the heat energy from heat to be changed into the electricity and so on. And last is the refrigeration, basically almost similar with the air conditioning and also heating system. Heat and other forms of energy. So as we all know, energy can be change form. So basically these are the numbers of form of energy, which is thermal, mechanical, kinetic, potential, electrical, magnetic, chemical, and also nuclear. And the sum of all this energy is the total energy. Let's say we have all this type of energy in certain system, so we need to consider all this energy in our calculation of energy. Okay, we also need to know a few terminology in the energy, which is the internal energy, which is coming from the kinetic and potential energy of the molecules. Sensible heat, which is the kinetic energy of the molecule that we can sense by our hand. Okay, so the temperature change and everything is the sensible heat. And then we have latent heat, which is the internal energy associated with the phase of the system. If the system change phase from liquid to solid or solid to liquid, it release certain amount of energy, which is being called as the latent heat. And we have chemical bond energy from the backup of chemical bond, it release certain energy. Is the internal energy associated with the atomic bond in molecule. And last is the nuclear energy. The internal energy associated with the bond within the nucleus of the atom itself. Okay, another terminology that being used largely in heat transfer and also thermodynamic, which is the specific heat of gases, liquid, and also solid. So the specific heat is basically the amount of energy needed to raise any body by 1 degrees of temperature. So that is the definition of a specific heat, and it has two kind of specific heat, whether it's at a constant volume or at a constant pressure. So from these two kind of specific heat, we know that the specific heat depends on two properties, which is pressure or temperature. Okay, pressure and temperature lah. So another thing that we need to know is at low pressure, all real gases approach ideal gas behavior. So the specific heat will be depend on the temperature only. So energy transfer. So we need to know first how energy being transferred. So energy can be transferred to or from a given mass by two mechanism. Okay, whether by heat transfer and also works. Okay, so there are another terms that you need to know also: heat transfer rate, which is the amount of heat transfer per unit time; heat flux, the rate of heat transfer per unit area normal to direction of heat transfer. Okay, so heat transfer rate is per unit time. Heat flux is based on surface area. Okay, power is the work done per unit time. The first law of thermodynamic. So basically, we already know that all things follow by this thermodynamic. All energy forms, okay, follow the thermodynamic law, which is energy cannot be created nor destroyed. It can only be changed form. Okay, so from this first law of thermodynamic, we can do energy balance equation, which is the total energy entering the system uh, minus the total energy leaving the system should equal to the change of energy in the system. Okay, so we can write this equation to be in the energy form, which is this is the energy in the system, and this is the change of energy inside the system. Okay, so if we divide it by time, or the period time taken for the process to happen, we can get the energy balance in the rate form, something like this. Okay, in heat transfer problem, it is convenient to write a heat balance and to treat the conversion of nuclear chemical energy and electrical energy into thermal energy as heat generation. So, as you can see in this equation, we have this net energy, which is here. Okay, the total net energy, net heat transfer, which is total energy in minus energy out, plus the heat generation from the other source of energy, or the summation of other type of energy. So the summation of all this is the thermal change of thermal energy of the system. Okay, something like this. So this is basically the energy balance equation for the system that related to the heat and also other source of other source of energy or other form of energy. Okay, energy balance for closed system, fixed mass, which is so this is basically revision of thermodynamics. Okay, a closed system consists of fixed mass. Okay, the total energy for most system contained in practice consists of the internal energy. Okay, this is especially the case for stationary systems since they don't involve any change in their velocity or elevation during the process. So there is no mass in, okay, and mass out. So there will be no energy coming due to the mass, only from the heat. Okay, as you can see, stationary closed system, the energy balance equation is something like this. As you can see, energy in minus energy out, and it's equivalent to the internal energy. And we can calculate this by using this equation, which is mCp, which is CV, sorry, which is the for the sensible specific heat of the constant volume process, and the temperature difference. Delta T here is the temperature difference. M is the mass of the system. So stationary closed system, there is no work because the system is closed. So the energy is can be written as this equation. Q is the energy or the heat is equivalent to M, which is the mass. CV is the specific heat at constant volume, and delta T here is the temperature difference, initial and also final states. Energy balance for steady flow system. Okay, another method of doing analysis of thermodynamics is based on the control volume. Okay, so in a control volume, basically we just set a boundary layers or invisible layers, something like this, and we do the analysis inside this control volume. And in normal cases, most of engineering device we use control volume as the method of analyzing the condition inside of it, or the energy in and out of the system. Okay, so normally we set it to be in a steady condition. Okay, steady operation condition. In the term steady mean there is no change with time at any specific location. Okay, another terminology that you need to know is the mass flow rate, which is the mass the amount of mass flow inside and outside, in and out of the control volume. And volume flow rate, the amount of volume flowing through the control volume. So this is basically the related equation. This is the mass flow rate equation. M dot is the mass flow rate. The unit is kg per unit second, and we can calculate it based on the density, velocity, and also cross-sectional area of the ducting or pipe. Okay, and then we have this volume flow rate, V dot, which is equivalent to M dot, which is the mass flow rate over density, or we can also calculate it from the velocity times the cross-sectional area. Okay, so the unit is meter cube per second. So another equation, this is the heat transfer rate, or rate of energy in. So m dot is the mass flow rate, delta H the enthalpy, change of enthalpy, and Cp here is specific volume, sorry, specific heat at a constant pressure, and delta T is the temperature difference. Okay, surface energy balance, basically just a theory related to the heat transfer. Okay, so surface does not have any volume, so just a sheet, or we can call it as viscous system. whose energy remain constant during a process. So it does not contain energy because it does not have any volume. So the energy in and out of this control surface is normally equal or same, and we can write the energy balance equation to be something like this: E in is equivalent to E out, and we can also rewrite the equation. Let's say energy come from a certain value, which is the Q1 here, okay, conduction, and then when it goes through the layer of this, which is the control surface, as you can see here, Q1 goes through this layer, which is the control surface, and it change into two types of energy, which is radiation and also convection. So the summation of Q3 plus Q2 is equivalent to Q1, which is given by this equation. Okay, this is the end of part 1 video. So what we already covered in this part is the relationship of thermodynamic and heat transfer, the terms, related terms in heat transfer and also thermodynamics. Okay, the first law, second law of thermodynamics, the energy, heat is the energy, so it can be only transferred from one location to another location through the temperature difference, and always from high temperature side to the low temperature side. So basically that's what we already cover in this part. So that's all. Thank you. Hopefully help with your study.